Hello and welcome to this video on dimensional analysis. Here we're going to walk through two simple examples. The first of which is quite straightforward, and the second of which is only slightly more complicated. Let's begin. In the first, we are asked to convert a blood lead concentration of 10 micrograms per deciliter to units of milligrams per liter. Let's do it. Begin by writing down the starting concentration, 10 micrograms of lead per deciliter of blood. So our job is to convert the denominator from deciliters to liters and the numerator from micrograms to grams, or milligrams. Let's begin with the denominator. There are 10 deciliters in every liter. Similarly, there are 1,000 micrograms for every milligram. Let's examine our units here, see if there are some that we can cancel out. Indeed there are, because we have micrograms in the denominator, micrograms in the numerator. We also have deciliters in the denominator and deciliters in the numerator, leaving us with milligrams per liter. Perfect. Let's multiply the values in the numerators. 10 times 10, we have 10 to the second milligrams. And examining the denominators, we have 1,000 liters. All right, 10 to the second milligrams per 1,000 liters. Let's simplify this a little bit by dividing the numerator by the denominator, and we are left with 0.1 milligrams of lead per liter of blood. So in words, 10 micrograms per deciliter is equivalent to 0.1 milligrams per liter. Let's move on to the second exercise. Here, we are asked to express that concentration of 0.1 milligram per liter in units of parts per million. So let's pause and think about what a part per million is before we proceed. A part per million is a mixing ratio. A mixing ratio is a unit of concentration in which the denominator and the numerator have exactly the same units. Thus, it's a ratio. So our strategy to address this question is to put both the numerator and the denominator in the same units. We're given a little factoid here to help us, and that factoid is: assume the blood has the same density as water, which of course we know is 1 gram per milliliter or 1 kilogram per liter. So let's get started. We begin with the concentration of 0.1 milligram of lead per liter of blood. And again, we want to get the units of the numerator and the denominator to be the same. We could choose any units, doesn't really matter, but for convenience I'm going to choose grams. So we're going to aim for grams of lead per gram of blood. Let's start with the liters of blood and convert those to grams. So every liter will have 1,000 grams, which is the same as a kilogram. So when why? Again, because we were told in this problem to assume that blood has the same density as water. So 1 liter per 1,000 grams. Let's put the milligrams of lead in units of grams. So we know for every 1,000 milligrams there is 1 gram. So let's examine the units now, see if there are any we can cancel out. And yes, there are. milligrams in the denominator, milligrams in the numerator, those cancel out. We have liters and liters, those cancel out, so we are now left with grams of lead in the numerator and grams of blood in the denominator, which is exactly what we want. So let's go forth and just calculate the product of the numerators and then the product of the denominators. Starting with the numerators, we have 0.1 gram of lead and in the denominator we have 10 to the third times 10 to the third, which is 10 to the sixth, so we have 10 to the sixth grams of blood. Alright, grams in the numerator, grams in the denominator, we have a mixing ratio. Perfect. Is that mixing ratio scaled to the extent that we want? Let's say we are asked to provide a mixing ratio in parts per million, so that means we want the denominator to have 1,000,000 parts, and indeed it does, 10 to the 6 grams. So 0.1 grams of lead per 1,000,000 grams of blood is equivalent to 0.1 part per million. And we could add a little notation here and say based on weight mixing ratio. That's what the W stands for.